Um, okay, so welcome everybody to, yes, to our to today's session of the IAMP seminar. If you're joining for the first time, this seminar is organized by the International Association of Mathematical Physics and takes place online approximately every 2 weeks. If you're interested in other activities of our association, you are very welcome to visit our webpage. So today we are very happy to have here Luca Fresta from Roma 3, who is going to explain something on local dynamics of extended Fermi gases at high temperature. High density, sorry.
Thank
Okay,
you.
thank you.
Thank you, Margherita, for the introduction and to all the organizers for the invitation. It's really a pleasure to be here in front of this audience. And yes, what I'm going to talk today is about some results about the effective descriptions of the quantum dynamics of extended Fermi gases at high density. And this is based on joint work with Marcello Porta from SISSA, Italy, and Benjamin Schlein from the University of Zurich. So this is not working. Yes. So let me start from textbooks, quantum mechanics, because Fermi systems are system of quantum particles. So to describe in quantum particles, the kinematics is as follows. So a state is described by a wave function and in the Hilbert space of L2. And for I will fix three-dimensional space for now on, while observables are self-adjoint operators on it. And so a quantum particle is intrinsically random. And the connection with probability having fixed a state and an observable is that we can take the expectation of the observable in the state phi, and it's given as follows. And in particular, it also gives us some, by the representation theorem, some probability measure. The typical example is that we want to measure the position of the particle, and the probability density is given by the modulus square of the wave function. So this is the kinematics, and yeah, so the list of a physicist would tell you the next step is the dynamics, which is given by the Schrödinger equation, where h bar is the semiclassical parameter and h is the Hamilton operator, which consists of a kinetic energy. Typically, it's given by the multiple of the Laplacian, but I will also be considering pseudo-relativistic systems for which the kinetic energy is as follows. And then there is an external potential, which is a function of the position operator. And in the typical system, this function is trapped in the system, say in a region lambda of R3, and outside of this region is going quickly. So to consider more particles, the prescription is very peculiar in quantum mechanics than what we have in 3D, either fermions or bosons. And this basically boils down that the wave function to describe a system of n particles is not just an element of L2 of R to the 3n, but it also, in the case of fermions, satisfies these constraints. That means that the wave function is totally antisymmetric, namely that on the permutation of the argument, it picks a sign depending on the permutation. And so this finally leads to the setting that we want to describe, which is this quantum dynamics for n interacting fermions in some arbitrarily large region lambda and at high density. Such a system will be described by a Hamilton operator of this form, where the first part here, it's basically like n times the Hamilton operator that we saw for the single particle, namely, so this acts on each of the coordinates of the particles. This is Laplacian with respect to the jth particle, and this is the position operator with respect to the jth particles. But because the system is interacting, we can simply put a two-body interaction, which For simplicity, we will take to be as nice as possible, smooth and decaying, and our range of order 1. And the lambda here is the coupling strength of the interaction. Now, by the way, the typical physical systems for fermions is a gas of electrons in, for instance, a solid, or possibly in the more modern systems, some cold atom gas that it's suitably tweaked in such a way to exhibit the Fermi statistics. But of course, you might say that, well, typically this interaction might be Coulomb, but the truth is that effectively the interaction is always screened, so it's quite reasonable also for physical system to consider an interaction of this type. And the quantum dynamics is of the typical problem. Basically, one lets the system relax so that the initial state is going to be close to the ground state of the Hamiltonian. Ground state meaning that it's the system with the lowest energy. And then to see a non-trivial dynamics, one perturbs changes some parameters in the Hamiltonian, for instance, by removal of the trap, and observes a non-trivial dynamics. So the Hamiltonian I wrote here actually can be taken to be self-adjoint on the Hilbert space, and then the solution of this initial value problem is very simple, and it's given as follows. But the truth is that behind this very simply looking solution, there is a lot of complication, and it's due to the fact that if we consider n very large, so in our cases it should be 10 to the 20 or more for solids, or 10 to the 8 for the cold atoms. This is basically a tragedy, because these objects really lived in huge spaces. So the basic message is that, okay, once we have the generator, it's relatively simple to write down the solution of the Schrödinger equations. But this is not very useful. And the idea behind effective descriptions is that we try to look for the dynamics of less of an object that has less information, but then it's going to be a nonlinear dynamics. But before doing this, digging into the details of this, the truth is that for general arbitrary h bar and lambda, this is still a very complicated problem. This is why people also consider some specific choices of this further parameters. And this is what I meant in the title with high density regime. Which means, first of all, that I'm considering a semiclassical high density, joint high density scaling. So the density rho is very large, and basically we're going to take h bar depending on the density. Now, this may look counterintuitive, but it can actually be grasped as follows. Now, for simplicity, think of the free system. So you have the system described just by the kinetic energy, and just take a system in a box, for instance, with periodic boundary conditions. Now you can really study in detail the systems, and because of the Fermi statistics, because the wave function is totally antisymmetric, then the ground state with n particles, so these n particle will have different energy, and eventually what let's say they kind of they form what is called a Fermi ball. If we take a chemical potential, so we're thinking of controlling the number of particles with a chemical potential, and this chemical potential is independent of h bar, then the computation of the density is basically this integral, or in 3D, and gives h bar to the -3. And in particular, it's an integral over the Fermi, so it's the volume of the Fermi surface, and this surface, sorry, the volume of the Fermi ball, and this ball has a radius rho to the 1/3. So in this scaling, what are the power counting of the kinetic energy and the interaction? Well, the kinetic energy can be computed as follows. And basically, if I have n particles, it means that for each particle, I have the prefactor h bar square, and then I said that particles go up to so they fill this ball, and so the largest momentum is ordered to the one first, so that the energy is going to be of this order. On the other hand, the interaction in this power counting is going to be proportional to lambda, and then each particle is going to see a volume of order 1 because this is let's say has a range of order 1. But how many particles are there in a volume of order 1? Rho. So in this natural scaling, what happens is that the kinetic energy has this power counting and the interaction this other power counting. So the additional and final constraint that we take is to be in a weakly interacting limit, which is basically the prescription that the coupling constant in front of the interaction makes these two terms of the same order, and this can be achieved as follows. So the quantum Hamilton, so the Hamilton operator I'm going to be considering in the high density regime, it can be written as follows, where you should notice that there is this h bar to the power of 3 here. And the power of 3, of course, depends on the fact that we're on 3 dimension. Now, there is another no, first, let me say this. In this regime, high density, I'm not talking about what the volume is. And in fact, this is interesting because you can possibly take it to infinity. And because the volume is arbitrary, h bar and end are independent. But there is another very so important and particular case of this high density regime, which is called, which is the mean field regime, and basically boils down to fixing the volume to order 1. And in such a case, one has this additional constraint. But again, the main question is about the effective description of the dynamics. So what do we expect? Well, basically, I'm telling you that I'm considering a system in a suitable scaling which is weakly interacting. So it's also quite natural to guess that the correct descriptions should somehow be close to the free one. Free one meaning that there is no interaction, but because of the Fermi statistics, actually, what is free should be called quasi-free, in the sense that it's not properly factorized, but it's factorized up to the symmetry constraint, and namely means that the wave function, the so-called factorized wave function in our totally antisymmetric Hilbert L2 space are let's say wedge products of some wave functions, and so this is the notation I use for what are called Slater determinants. What does this mean more in detail? Well, as you expect when you have such a description, in a sense, the wave function contains, so you don't need to go to a larger Hilbert space as n increases. And in fact, it's enough to consider a marginal of actually the projection associated with this wave function, and this marginal is called reduced density matrix, which for a Slater determinant of this form is just a rank n projection. And notice that this guy determines all the information on the systems, namely if I want to know like the probability density of small n particles, so meaning that I'm tracing out all the remaining particles being in some position x of r to the 3 small n. This is just given in terms of this guy by this and the density is the determinant, and this is why such states are called Slater determinants. By the way, I'm not having a look at the chat, but please stop me if you have questions. And what's been established is that at high density, actually factorized, so quasi-free states are really good. This has been proven first at the level of the kinematics, in the sense that the ground state energy is well that I denote in this way. It's well approximated by the energy that you obtain, the so-called Hartree-Fock energy, which you obtain by considering the variational problem, in which you restrict to wave functions of this type. So stated otherwise, basically there exists a later determinants that has an energy which is very close to the ground state, and this was proven for atoms, for large atoms and molecules by Bach, and then extended to the gallium, which is basically a system of electrons in a uniform background at high density by Graf and Solovey. And it's also worth mentioning recent progress about the computation of this difference in the mean field regime, as a series of authors in recent years obtained the following expansion with C optimal constant. So this was basically what we know about the kinematics. And when it comes to the dynamics, well, the idea is again to kind of restrict to the single particle description by looking up these objects. And when we try to follow these objects, the dynamics that emerges is the so-called Hartree-Fock evolution, which is again a unitary dynamics. But this time the effective Hamiltonian is time dependent and is basically self-consistent, because not only you have the kinetic term, but instead of the two-body potential, there is an effective potential, which is given by basically by the density at that time given by the state itself. So stated in a sense, what you should picture in your mind is that because the system is a high density, a particle moving in this Gauss of high density sees an average potential which is mediating all the effect of all the particles, and in a sense it's canceling out some of the direct effect, and this is why it's believed to be accurate. And this is sometimes called a Markovianity property, and it's really the fact that it doesn't matter what the system was in the past, but instantaneously there is an effective description that can emerge. And before moving to the general high density regime, I want to mention some results about this effective evolution for the mean field regime. Now, again, let me flash briefly how specifically the Hamiltonian mean field regime looks like. So, because we have this constraint, the coupling constant here is 1/n. And when you let the system relax to the ground state, you expect the ground state to basically have the following semiclassical structure, that it's basically captured by the following products, where you should think of this as being the density of the system, that it's nice and mildly varying, and whereas off the diagonal you have some decay, which it's basically in terms of h bar, and so when h bar is very small, this decay is very fast. Now, effectively, this structure is bound with a commutator with respect of, let's say, the position operator, and with respect to the semiclassical
we lost you on the I just lost you for a two set. So you were at the semi-classical structure, and then you were talking about the phi, and then I lost you. Don't know, maybe the others, it was maybe only my computer. Maybe you can just
sure.
The phi. You were just there at the phi, yes.
Yes, so the phi is decaying, and because of this this ratio means that decays fast as h bar goes to 0. So it's an operator that it's concentrating along the diagonal. But now one can prove that a structure of this form actually implies some commutator bounds that have now become well known in this business. And it's basically, even though I didn't write it this way, but it's basically the trace norm of the commutator with the position operator and the trace norm of the commutator with the semiclassical momentum. And a proof of this has been given in the following work. There have been a lot of results of the mean field regime, but probably the most important and also the simplest one is this one by Benedictor, Porta, and Schlein, in which is as follows. So basically, you take omega to be a rank n projection, having the semiclassical structure in the sense that it satisfies these bounds. Then you take a wave function whose reduced density matrix is exactly this omega, and you let it evolve via the quantum many-body evolution. And then you take once this is evolved, you take again the reduced density matrix and you compare it with the evolution of omega under the Hartree-Fock evolution that I showed in the previous slides. And if you the two dynamics are close in the following sense. So in the Hilbert-Smith and trace topology. Now, why are these good bounds? Well, it's because the size of this object is very big, depending on n. Another thing to bear in mind is that, okay, they consider the Hartree-Fock evolution, but the exchange term that was appearing here, and I basically kind of skipped earlier, it's subleading and it's not that important in this level. Now, I mentioned this result, but there has been a lot of work starting from the pioneering work of Spohn and Nanufa Sewell. In particular, over the last, I would say, starting in the early 20s, so where people obtain a lot of results by varying the setting in very different ways. So like by considering regular potential, singular potential, mixed states, and further changes, and with a lot of improvements from one results to the other. I'm gonna skip this to read this in detail, but it's just for you to have a like an overview of what's been done for the mean field regime. But on the other hand, in the general high density regime, in which the volume can be arbitrarily large, there aren't so many results, and this is what I want to present. So for first, I want to present a global convergence result. So what's the setting? Now let me stick to for simplicity to pseudo-relativistic fermions. I'm gonna come back to this on why I make this choice. And the basic idea is that the high density regime locally in every volume of order one, it's really a mean field regime. So what does this mean? Well, it means that locally we kind of need to have the same semiclassical structure, and this is what can be encoded in the following bounds. So I see a message in the chat, new message, no?
You don't have to care about this.
Okay. So in particular, to grasp, let's say, volume of order one, let me introduce the following operator that you should think of as being like an operator that localizes thanks to the fast power law decay in a region around Z. Then also introduce this weight that it's useful to kind of say that the system should be in a volume should be localized in a region lambda. And basically, local semiclassical structure could be encoded in the following bounds, where the first bound is basically telling us that the density should be of h to the -3, while the other two bounds are again commutator bounds and are a local version of the ones that we saw in a couple of slides ago here. The main difference is that now the system is in an arbitrarily large domain, and we don't want to have bounds with respect to the number of particles, but only with respect to the density. Why? Again, because possibly we send the volume to infinity by keeping the density constant. Very big, but constant. And this is why this one necessitates to have a local bound. And yeah, so whereas the previous commutator bounds I described have been proven, at least in some situation, there is currently no proof that let's say the ground state of such a Hamiltonian should satisfy these bounds, but one can check that at least for the free Fermi gas this is true, and this is also true for a coherent state approximation of the ground state. And the theorem for such a case is as follows. So take the two-body interaction to be smooth and decay. One small omega Rankine projection satisfies, in this time, the local semiclassical structure in the sense of these free bounds here. And you take a wave function with n particles such that its reduced density matrix it's equal to omega, or it's close in some way that I might make precise later on in the proof. Now you let omega.
Luca,
yes.
Sorry, may I ask a question here? You said you're taking the infinite volume limit.
No, I didn't say that. No. No. So thank you for this question. No, I present the results that is uniform in the volume. So we don't consider a priori as an infinite system, but we want everything to be uniform in the volume.
Did you say you increase the volume at the same time you keep the density constant?
Yes, in a sense, you can take density constant and the volume as large as you want, but the result I'm going to present is for arbitrary but finite volume.
So in other words, you fix the volume, but then you can keep it. I'm trying to understand this. Is there a limiting procedure here? That's what I'm trying to understand.
No, in the volume, there is no limiting procedure.
All right, thank you.
Thank you. Thank you for your question. Yes, and again, similarly, so omega OT solves the Hartree. So this time I'm just dropping for simplicity, the exchange term. So the Hartree equation, which reads as follows. With initial data omega, and on the other hand, I look at the quantum many-body evolution. So here there is a minus. And then what we can prove is that, again, once I trace all the particles from this wave function, so I consider the reduced one-body density matrix, the closeness of the quantum evolution can be proven in this sense. Now, so we have a bound in the Hilbert-Schmidt and the trace norm. First of all, why is this a good bound? Well, because this convergence rate, now convergence in the sense in h bar, because the size of the object, for instance, here are, so the object, the Hilbert-Schmidt norm of this guy or of this guy are of this size, whereas here is of the size n. So basically what we gain is a factor of square root of h bar. So in this sense, this is a convergence results, because it's as if h bar is small enough, this or is possibly sent to zero, this is gonna give convergence. I presented the result for pseudo-relativistic fermions. What about non-relativistic fermions? Well, we can prove a similar results, but there is a further constraint, is that we cannot have this evolution for, we cannot follow the evolution for all the time. We have to stop at a certain threshold time, capital T star, which is independent of h bar, but let's say depends on other details like what the two body interaction is. And in this case, also the same bounds hold. Now, why do we have this limitation? Well, we have this limitation because we don't know whether the Hartree dynamics has some concentration. So why is this a problem? Well, again, the Hartree dynamics is unitary. So as long as we can make sense of the generator, we have the evolution. But we can make the sense of the generator means that we want this to be nice enough. And basically, this boils down to having the density that does not explode at one point. And the problem is that in our estimates, we cannot rule the concentration of rho at arbitrary large time. So we don't know if the dynamics is going to concentrate the particles in one point, the Hartree dynamics, and if this happens, it means that the Hartree dynamics is no more defined. Some related work in this regime was done recently, and to the best of my knowledge, basically, besides the results I'm presenting and these other works, probably there aren't other results in this high density regime. So it's a little bit so we're considering let's say this result is still, it's nice, but it's a bit unsatisfactory because here there is a constant, not a constant, but a volume factor. So in particular, the one would like to understand, this has to be there. It's not surprising because we're considering this topology, but the idea is that in principle, one should not care about the whole system. The interesting part is that one would like to test the two dynamics locally. And because we look at this global topology, we pick up the total number of particles, which is proportional to the volume. And this has led us, so this motivated us to look at also the proof of or obtaining some results in some local topology. And the first result I'm going to present is about the case of the zero temperature. And the basic settings is a little bit different. So what we do is that we're thinking of the system that let's say it's in the ground state of a one-body Hamiltonian. Sorry, this is a typo. This is capital H. So consider a Hamiltonian of the following form with some external potential, and what we assume is that the external potential is nice and smooth and grows at most quadratically at infinity. And furthermore, it is such that for some chemical potential mu, the following bound holds for all the z that are in a ball around z0 of a radius like this. So basically, if you look at this, this is could be considered as a local Weyl-type estimates, and is it's basically saying kind of counting the states in a shell around in a shell of size h bar around the Fermi surface. Now, is this bound reasonable? Well, first of all, it's relatively easy to check that for free pseudo-relativistic fermions. So you take capital H to be this, then you want to compute this, and with some basic manipulation, you can prove that basically it's bounded by the L1 norm of this guy and this guy. So this guy is chosen in such a way that it's integrable. So this is of order 1. On the other hand, this is precisely what I was describing. So we have a weight here that it's basically localizing in a shell of thickness h bar around the Fermi ball, and we lose h bar to the -3 because that's the density. But otherwise, because we restrict to a shell of size h bar, we gain 1 h bar. So this h bar, so this bound is actually very reasonable because it's true for pseudo-relativistic fermions, but it's also true for in the case of the presence of an external potential, and in the case in which this external potential is confining the system in a region of lambda of order 1. As this
Luca,
was proved. Yes?
yeah, sorry. Could you, is it a reason why you used L1 norm, and could you prove this inequality for like L2? And would it be insightful to try to see what other norms would give you? Like,
You mean this norm or this?
the inequality, yes.
Well, but the inequality. So I mean, the thing is, so this is the trace norm, and as a matter of fact, you can think of this as okay, up to commutators, I can take the square root of this and put it here. Once I have this, I have a positive operator. So to reach this manipulation, I'm making mistakes of lower order, and then let me compute this. But when I compute the trace class norm, this is equal to the trace. And when I compute that trace, I get exactly this as an equality. So the thing is, yeah. So basically, up to lower order terms, this is basically an equality. So I understand your question, but this is quite optimal. It's not like I'm making some mistakes. Yeah. But yeah, this is a computation for free fermions, but for, sorry, in the case of free pseudo-relativistic fermions, but in the more general case, one has to use semiclassical analysis, and this has been done in these papers, but it's been done with, let's say, a volume of order 1, and for the case of non-relativistic fermions. In particular, here we don't want any dependence on the volume because of what I was saying before, that basically the whole business is to try to get rid of constant depending on the volume. And as I said, this is basically meaning that we're looking at the ground state of a non-interacting Hamiltonian, so that the ground state wave function could be written in this way, and that the one body reduced density matrix is the Fermi projection. But the truth is that this could also be applied to interacting fermions by looking at the effective description via the Hartree potential, because the Hartree potential has additionally a term of this type. And one can actually prove that if one can prove these bounds for the non-interacting case, this bounds would also would also hold for the minimizer of this Hartree function. And the results in this setting is as follows. So take H satisfying such local Weyl-type estimates and the two-body potential as nice as possible. Take away function psi, and such that its reduced density matrix is basically the Fermi projection associated with this H below the chemical potential mu. Once more, omega of t solves the Hartree equation, while psi of t is, again, there is a minus here, it's the quantum many-body evolution. And now we want to look at a local topology. To do so, we take an observable O, which is sufficiently nice and has a range O as a range of order 1, and then what we can prove is that the trace so of this difference against this operator that it's localized in a volume of order 1 has the following bound. And this is a bit technical, but this holds for any t smaller than r. What is r is this, it's basically dictates the size of the ball where we made this assumption. So if this assumption holds everywhere, this results holds for all the times. Now, once more, h bar is small, right? So is this bad? Well, no, because this should be compared to the these other objects, which basically are proportional to the density, and the density is h to the minus 3. The other remark I want to make is that I'm not going to state any result for the non-relativistic case, because there is an important difficulty present, and it's about the unbounded group velocity. And this basically enters the fact that we don't have any way to control commutators of this form, because these objects are unbounded in the quantum dynamics. So whereas in the other results here, there was a result for non-relativistic fermions, but it was up to some T star because of problems with the Hartree dynamics. Now we start already seeing some problems at the level of the quantum dynamics, and this is basically it's more involved. On the other hand, a simple remark is that, okay, what about lattice systems? Well, lattice systems have naturally a bound on the group velocity given by the lattice spacing, and so even though we didn't write it down, but this result should apply to lattice systems as well. Now, to prove this result at 0 temperature, we actually used let's say a more general result about mixed states, and the idea is that what we do to prove this result is that we approximate the ground state with a thermal state and then let it evolve and then compare the two dynamics. But the result itself for a mixed state is interesting, and to describe it, I need some more notations and notions. So first of all, not only we consider so temperature different than 0, but it's easier to work in the grand canonical setting. That means that the number of particles is not fixed, but it's random. So since the number of particles is arbitrary, the natural description, or let's say lift of the n-body description, is in Fock space. So the Fock space is just the Hilbert space direct sum of all the Hilbert spaces with n particles, and so a wave function in the Hilbert space is a collection of wave functions like this. Then one can also lift operators. So if I have one operator O acting on my Hilbert space, the Hilbert space of the single particle, I'm going to denote by d gamma of O its second quantization that acts as follows on each of the components. So basically, it's it's sum of objects like this, where basically the O acts only on the Jave particle. And now let me also introduce this other notation, which is the lift for two-body operators. It's similar. So this time, so when it acts on a n particle wave function, one has to sum over all the pairs, and then you have that V only acts non-trivially on the pair I and J. So in this setting, the Hamiltonian we were looking at is precisely the second quantization of the kinetic energy, and then we have this lift of the two-body potential. And when we talk about mixed states, it just means that we're looking at density matrix on the Fock space. So operators satisfying this bound and normalized. A typical example of a mixed state, for instance, are free Gibbs states. So it's a mixed state, so identified by two parameters, beta, which is the inverse temperature, mu, the chemical potential, and are proportional to this. There is a minus here missing. And well, in this setting, one can again talk about the reduced density, which basically means, okay, once more to trace all the particles but one. And so when we try to compute the expectation of some observable, which is the lift of a one-body observable in the density matrix rho, this basically is equal to tracing the observable all with respect to this guy, which is called the reduced one body density matrix, which, by the way, has normalization n. So the total number, the average, which is the average total number of particle in the density matrix row. Again, the example is if I'm taking my free Gibbs state and I do this reduction, the one body density matrix is a well-known Fermi-Dirac distribution, and I inverse temperature beta, and when beta is infinity, this reduces to the Fermi projection. So the assumptions that we need in this more general setting, or let's say if we want to prove some convergence in a local sense, is again based on the local semiclassical structure, but requires more assumptions. Namely assumptions also on the decay properties of our reduced density matrix. Now, this might be a little bit overwhelming, but let me go through this slowly enough. So with respect to, let's say, what we assumed, let me go back quickly. What we assumed here, where there was only one localization operator, so basically now we're making assumptions with two localization operators. Now just forget about the power. And the important thing is that we basically also require that if we are looking at, let's say, omega z on the left and wz on the left and wz prime on the right, we also observe decay. And yeah, so this is why. So this generalizes the assumptions on the density, and these two guys generalize the assumptions on the commutator estimates. Again, commutator estimates, let's say with respect to the position operator and with respect to the semiclassical momentum. Now, for technical reasons, this has to be assumed not only for omega, but for thermal states, we also need the square root of omega and the square root of omega, sorry, 1 minus omega. And furthermore, we assume the following bound, on which I'm going to comment in a second. Yeah, so the reason why, as I was mentioning, we proved our result of zero temperature by using mixed state. It's because we don't expect that let's say the Fermi projection satisfies these bounds. So in general, well, you can take the free case once more, and if you do the computations with the free case, so you take the Fermi projection of the free case, you can ask yourself, okay, do these bounds apply to the free case? And the answer is that unfortunately, what you obtain is that this guy is decaying, and as I was saying, but it's decaying slowly in a non-integrable way. And this is not surprising because this is non-smooth in momentum. So this is the biggest problem, that we want a decay which is strong, integrable, but that a zero temperature might not be realizable. And this is why we're thinking of mixed state. The other comment is that a requirement like this is basically measuring the overlap of square root of omega with square root of 1 minus omega, and it's basically telling us that the mixed state we're considering are at low temperature. And last but not least, it's the whole idea of the reason why we looked at mixed state is that if capital H satisfies the local Weyl-type estimates that I stated here, so we have capital H that satisfy these estimates, well, then if we look at thermal states with temperature over their H bar, then these objects do satisfy these bounds. And this we prove in work. And so taking these as general assumptions that we make on the initial states, we can state the following theorem. So in the pseudo-relativistic case, you take the two-body potential nice, and you prescribe that it is a trace. So you take omega. Now it doesn't have to be a rank n projection. You take it such that it satisfies this bound. So basically it has density h to the minus 3, but also it satisfies these assumptions. Then denotes the omega t once more, the Hartree evolution. But now you take a density matrix on the Fock space such that it's reduced density matrix is omega, and you let a rho evolve via the quantum evolution. Again, the signs are wrong. And once you do this, you again reduce consider the reduced one-body density associated with this rho, and the result that we prove is as follows. And once more, and we have the same convergence rates as for the previous result. Just some brief comments. I didn't mention mixed states in the case of global topology for the convergence, but one can also prove that in principle and obtain bounds like this for mixed states. And the other thing is that the work on mixed states is based on the Arakivis formalism that was previously used in some related work in the mean field regime in this work. And this is all I wanted to say about the results. Maybe it's a good point to see if there are some further questions.
Yes, probably you said this, but you always have this factor C of t, which
yes,
is sort of
actually,
e to the ct.
Yes, thank you for this question. So yes, because we use Gromwell, we end up with constants like this.
Okay.
I want to point out that this is not an artifact of the high density regime. It's more of how the thing is proven, and was also the case in the mean field regime. So yeah, there is a bad constant. But yeah.
Is it? I mean, should it be there? I mean, is this here for technical reason, or you mean this approximation is that bad, really?
Well, if you think about it, in principle, when you consider this regime, what you expect is that so h bar is also the constant in front of here.
Yes.
And in a sense, you have a velocity which is of order of, it's this Fermi momentum rho to the 1/3. But rho to the 1/3 means h bar to the -1. So basically, you see that if you move for a time of order 1 and you have a velocity, a time of order h bar, and you have a velocity of order h to the -1, you're going to travel for basically 1, and this is precisely the interaction potential. So the answer is that you expect that the closeness should be at least for time of order 1. For general time, it's not so clear if you don't take the limit. Okay, so if you take h bar constant, you don't expect this to be always a good description. Okay, so you could state it in this other way. If you start from a Slater determinant, the quantum evolution will create correlations. So it will naturally destroy the factorization property. But because of what I said earlier in the scaling, you expect that for time, again, this time that I'm talking about, it's rescale. So for time of order 1, this is not going to happen. So at later time, this will kick in the real quantum evolution. So if you fix h bar, this should be spoiled. But again, if you take h bar to 0 before let's say taking t to infinity, then you have a meaningful convergence. Thanks. Thank you for this question.
Thank you.
So maybe in the remaining 5 minutes, let me say quickly convey some ideas from the proof. Actually, regardless of the setting, we always work in the Fock space formalism, which is quite convenient for a few reasons. First of all, Slater determinants can be written in this form. So A is the annihilation operator and H star is the creation operators. I don't have time to introduce exactly what they are. But not only this is useful because of this, the main message is that in the Fock space formalism, we can have a Bogoliubov representation of quasi-free states. Stated otherwise, one can find a unitary operator that it's implementing let's say the Slater determinant. So you start from the vacuum and then you can create a Slater determinant via unitary. Unitary are very useful transformation because they preserve norms and this is actually a very good property. Now, the Bogoliubov representation can be done only in the case of pure state, so rank and projection. So I'm thinking of omega being a rank and projection. This is why in the mixed state situation, one has to basically enlarge the space in such a way to make the state a projection. But this then introduces some more complication, and this is why for zero temperature you can think of U, which I'm going to be using in the following slides as 1 minus omega, and V basically as omega, let's say, but in general, in the mixed state formalism, these are as follows. But now, so why is the Bogoliubov transformation useful? Well, it's because it allows us to make this comparison with the Slater determinants in an easy way. In particular, the main object one should look at is the fluctuation dynamics, which means that, let's say, at time s, you create the Slater determinant associated with omega s, then you let this evolve by the quantum evolution. Sorry, this should have been, yeah, so this is correct. And then you kind of remove a Slater determinant, but this time you remove the one associated with omega of t. And so let's put s equal to 0 and look at the state, which is basically the fluctuation dynamics of the vacuum. And one can prove bounds like this. So if one looks at global topology, a bound like this can be proven. And if you look at the local topology, then, okay, so if I take this to the other side, I obtain exactly the expression I was looking at, but then besides subleading terms, one needs to control this object. So thanks to the Bogoliubov transformation, all this quantity that I wrote down can be controlled in terms of some many-body quantities. So how do we control these many-body quantities? We do it so we can prove bounds on the following form. And yeah, so the idea to prove it is by Grunwald. So we want to control the derivative, but taking the derivative means taking the commutator with the generator of the fluctuation dynamics. This generator consists of 3 terms. First of all, the second quantization of the Hartree Hamiltonian, which is, by the way, a term that commutes with the position operator n. Then another terms that commutes with the position operator, but it's quartic in these creation and annihilation operator. And last, a term q, again quartic, that is no longer commuting with the position operator. So in particular, if we look at the commutator of n with the generator, only this term matters. Whereas more generally, when we look at the local dynamics, we'd have to take the commutator with this, and then we have all the terms. Now, I want to mention that, let me first go forward. How do we treat the separate terms? Well, the first terms can be treated because because the group velocity is bounded, so that we have a general bound with a nice h bar factorial. Sorry, not factorial, h bar factor. To treat the quartic term, instead what we do is that we split our two-body potential as a convolution, and this is maybe not optimal, but it allows us to get rid of any volume factor. And so once we do this, after a lot of manipulation and, let's say, Cauchy-Schwarz inequality, we can bound the typical term appearing in one of the terms in the generators as follows. So again, you see that we have, you can think of V as being basically a localization operator, and this is why those assumptions are to be taken in order to control this. Now, if this were at time zero, this is precisely what we assume. But on the other hand, at time t, it can be proven that the local semiclassical structure is still present up to some constant, which is again exponential of the exponential. And so this is basically the whole idea, is that at the level of the quantum many-body, by Gromwell, this can be reduced to such norms of commutators, but at time t, but we assume that at time zero, but the Hartree dynamics is nice enough and propagates such bounds. And finally, as I already said, but I'm not going to go through this, the basic idea was that we can use the result about thermal states to approximate decays at zero temperature and to compare the two dynamics. And this is everything I have to say. Thank you for your attention.
Thank you. So if you would like to ask some questions, please just unmute yourself. Maybe please, Al.
Okay. Yeah, actually, I'm confused about the setting of main theorem, I think, which is theorem 2.
Yes.
So is this for the case with external potential or without external?
No. The typical problem. So the typical problem is basically the quantum many-body dynamics after the trap is removed.
Okay.
So the ground. We look at the ground state with the trap, but then the evolution. So with the Hamiltonian, I mentioned in the evolution is without the trap.
Okay, so this uppercase H appearing here is the initial Hamiltonian with trap.
Yes.
And you time evolve with Hamiltonian
exactly.
without external trap, but with interaction.
Exactly. So going to your question, so basically we look at the ground state of a Hamiltonian with a trap. Now, as I said, for simplicity here, I'm looking at the Hamiltonian without interaction. But as I said, basically this is also capturing the interacting case. And then we take the ground state of this guy, and we know that it satisfies this property. And then we provide a conditional result. Instead of just saying take the ground state, we say, okay, take the initial state that satisfies these properties, or let's say take the ground state, which is the Fermi projection associated with this Hamiltonian, and with this Hamiltonian satisfying those properties.
Okay.
Now, this is the ground state of a trapped system, and then we let it evolve without. So Hn here is where is it? It's this Hamiltonian here.
Right. Okay.
Yeah, thank you. There are a lot of H's.
The notation is not optimal. You should You
It's
should
not
call H like
optimal.
you should introduce like H trap and H free. Okay.
Yes,
Right.
you're right.
Yeah.
Thank you for your
Thank you.
question.
Yeah, that's now it's clear.
More questions? Maybe I had, so could you explain? I mean, you said it, but now I somehow I didn't get it well. So what is the advantage of introducing these the mixed state and these actually these um, right?
Yes, so let's say we want to prove this result.
Yes.
Okay, so for the ground state of a system. So you look at your quantum dynamics, you try to do this analysis because this is the goal. Let's say the difference of these two guys is what you want to control, and this is telling you to control this quantity. But once you control this quantity, we do it by Gromwell, and you end up, so basically, so again, by Gromwell, if to control this quantity, I want to control its derivative, but its derivative involves the generator. And as a simplification, let me consider just one term in this, so this one in yellow. Now with manipulations, you can prove that basically this contribution is bounded by h bar cubed times this integral. Now this integral, as you see, so this guy, it does not have any decay in z prime. Why is that? So you should think of this as basically being related to the could be controlled by yeah, let me see here. It's basically controlled by this.
Okay.
Why is it? Well, I wrote it in the so you have this, you can Fourier expand, let's say extract a localization operator, and then what you're left with is, let's say, e to the IPX. So in a sense, this guy, but the message is that this guy has the right power counting in H bar, but it does not decay in Z prime. So how can we do the integral? Well, we can do the integral if this guy has decay. But this guy has hope to decay because now there are two localization operators. Forget about the fact that it's in the commutator, but it's a quantity that depends on 2 points. And so the basic idea is that you can control this in this way without losing the volume of the system, without losing a factor that is the volume of the system, if this guy actually has an integral decay in z minus z prime. So when you carry out the many-body analysis, even for the zero temperature case, you end up with a bound like this. And you understand that you can really close your estimates if this guy has decay. Now, let's ask ourselves whether this guy can have decay. And this is where the comment about the mixed state comes in, because for mixed states, we expect that this is the case. I mean, we can prove it. You take these objects here. H is a nice Hamiltonian that is satisfying the local Weyl estimates, and our Fermi-Dirac distribution satisfies all the nice decays that we want. But what about a zero temperature state? Well, the zero temperature state has a discontinuity. So, and let's say if you think of the free pseudo-relativistic system, you have a discontinuity momentum, and if you have a discontinuity momentum, its Fourier transform cannot decay too fast. So it's not continuous, and so you cannot have an integrable decay. but the decay that we want has to be integrable. So this is why, in general, you could write a result like a conditional result, like, okay, take an omega that satisfies these, but the message is that typically an omega satisfying a decay property is a mixed state. And so we restated the result for mixed state. And then you can ask the question, okay, but if you have the results for mixed states, what can you say at the zero temperature? And this is my
So
last
you have
slide.
okay.
And the idea is that if you raise the temperatures just a little bit, so let's say you want to control this quantity where omega of t is the evolution of your the Fermi projection. Now you compare this with the evolution, the self-consistent evolution of the Fermi-Dirac distribution where you raise the temperature a little bit. So this is why you introduce this solution omega tilde of t. And then you have two problems. First of all, to control the difference of the two evolutions, but because you raise the temperature just a little bit, you understand that the two are close. And then you have the final problem that to compare the Hartree evolution of a thermal state with the quantum many-body state. But this is what we did do in the theorem. And this is why...
So the trick is that you let it evolve for a small time so that you're not very far from the initial state, but then you are smooth everything enough so that now you can start doing your arguments.
No, the time here is arbitrary, but we just raise the temperature a little bit, and then we let it evolve for any time. Again, as Hal was saying, here there are always constant that I'm hiding that explode in T.
Okay.
So this is expected, and the rate is not optimal, but the constant grows in T is expected.
Okay. Unless you send H to 0 first.
Exactly.
Okay. Okay, thank you very much.
Thank you for your question.
More questions or comments? Okay, if not, I will close the official part of the seminar. So we thank the speaker again.